So now we're gonna continue from yesterday's problem, where we will understand the remaining parameters how we're gonna calculate. So first we will the second one that we'll do is sensible heat gain sensible heat gain due to exposed glass. ఏంటమ్మా? లేదమ్మా అలా లేదమ్మా. స్టడీ లేదు కదా. Exposed sensible heat gain due to exposed glass. So first and foremost thing is sensible heat gain due to exposed glass. And first we'll start with north direction. North, north. So that is again, what is the formula for this? Q is equal to U into A into U into area into delta T, equivalent temperature difference, isn't it? If you remember, it's just because we'll get it according to our latitude for glass, so automatically we need not use any correction factor that I explained you yesterday when prior to that. So anyway, so Q is equal to UA delta T is nothing but the equation that you have got. So now we have to apply what is the U factor, A factor, and delta T. We have to calculate as per our data. So first and foremost thing is U factor, area, and delta T. So U factor for the glass, you have to get it as per the data sheet, and it depends on the type of material you are basically using. So we will consider some kind of dark color glass with kind of kind of a curtain or anything inside. Is it fine? Let's say the dark color of the glass is a bit dark, and I've got a blind inside, like a curtain, which is light color. Is it fine?
Yes, yes.
So considering those values, just a sec in the first, sorry, what was the trick? Uh, and where the data we have. Just a So in this, we have to refer to the U factor according to the material. So what is the U factor over here is to go to a particular page. Just a sec. Yeah. So this is latitude and all that will understand it again. This you'll get. I mean, this sheet will give you basically solar heat gain through ordinary glass. That is nothing but your this one delta T value. U factor of the glass. We have to calculate it. Just a sec. Yeah, you can see it. Overall factors for solar gain through glass. Yes or no? So, depending on the type of glass we have to choose. So, I've considered single pane glass, ordinary type. But let's say I've considered approximately the type of glass is, for example, not exactly dark also. I can consider even a medium as well. But inside I've got some kind of Venetian blind. So I can take your ordinary glass, but the Venetian blind is light color, I told you. You remember? Hello. Ordinary glass, if I take it, I'll consider the blind that I have it, the curtain kind of thing, whatever I have it, that is light color. So considering that, this value is 0.56. Understood? But similarly, depending on the type of glasses, you have certain things. Understood? For example, if it's a dark blue, dark red, according to the color of just the glass, also you have your U factors. So for this particular point, I'll consider ordinary glass, which is having a light curtain inside. So considering that, the value is 0.56 as my U factor. That is page number 12.
Mm.
Okay. What is it? Page number 12, I'll write it. Page 12. What is the value? 0.56. 156. Then coming to area. Area, as per the drawing, don't you think I'll be able to get it? So what is it? It's 15 into 8 in north direction or not? In north. It's one glass, is it? Which is equal to 15 into 8 feet. Then you've got delta T, that is nothing but equivalent temperature difference. So for that, we have to understand what is our angle of incidence. So for Bangalore condition, if you see, what is the latitude? It is around 12.58. You agree?
Bangalore.
It is 12.58 is the latitude for Bangalore. So considering that as the latitude, we have to choose our delta T value. So this value, we have to go for 10 degrees latitude, which is our nearest available one, right? So we to go for uh, this particular one, 10 degrees is at, I mean, 12 is obviously near to 10 alva. So we have to take 10 degrees.
Mm.
Now, which time do we have, high peak summer? Which time you will generally
First
have?
summer, May, June, May,
May to April. So either this
April to
zone
May. Yeah.
or this zone, any of this zone. You agree?
Mm.
Yes or no? So considering this
Yes.
north latitude, we have to consider either this or this. So you can just see the values actually. In fact, almost if, for example, at evening 4 p.m., if you see this zone, you have got a highest values. You agree? Majority of
Mm.
them. Yes, unless you have a skylight. So you will consider this particular one, which is your August and April, because April is peak generally what you have it. You agree or not?
Yeah.
We'll take this value. So in north, what is the delta T we got? It is how much? 16. You agree? This value
Mm-hmm.
is 16. And even this or this, we'll just check this one as well. Even this one is also a bit higher, but that's okay. South is 11. Here the south is 11. North is 39 in July to July, May, and then 130 northwest, horizontal 94 is southwest. Here the southwest is 66, 158 is west, 163 is west. So that's what, so either you take the above one or the below one. So we will take the below one. Is that okay? I mean, you have minor differences anyway. I agree. So shall we take the bottom one, which is April?
April. Or the time of the year.
Yeah.
April 2021.
Hello.
Mhm. Yeah.
Okay. So we'll take this one.
Yeah. North
So north is
16.
what is the temperature that we got it for August 24 to
16.
April 28. For north direction, the value is 16. Over
16.
here, this value is 16. Delta T is equal temperature difference is 16. So Q value. How will you get it? Q
0.56 into
Q value is equal
15
to
divided
0.56 into A into delta T.
into 16. Mm.
Right. So this I can write it as equation 2A.
Mm.
2A. Then I'll write sensible heat gain due to exposed glass in east as well. Just a sec. I'll write all the. Okay. So this value will get it in the north is done.
Mm.
Then coming to the next one, of course, A value, sorry, a delta T value will get it in page number how much? In our case, it is page
Mm.
number
16.
7. Already page number, so that
Thinking
next time
about it.
when I give you this, you'll be able to figure it out easily. Nothing else.
Mm.
See, B and capital. Yeah. Okay. Now coming to the next one is sensible heat gain due to exposed glass in north is over. So then
East.
don't you think it's east?
Yeah.
Yeah, exposed glass in east. So how many glass are there? How many glass are exposed for us
Three.
for our area?
Three.
Three glasses. Only these three glasses, right? Not these two, because this is not
Mm.
our area at this point of time, isn't it? It's a separate air
Mm.
condition, so we need not worry. So considering this, we have got only three glasses, which is 5 into 5, 25 square feet. So is equal to 25 into 3. That's our area. Delta T we have to see for east direction. So we have to see delta T east direction. What is the value? That's 11. You agree?
Mm.
Yeah. So this value is 11. East direction delta T is 11. So automatically we got this value, which is equation 2b. Then coming to sensible heat gain due to exposed glass in south. Same again. This one we can refer area. Have to change it obviously. So what is the area of this particular one in south? U factor will remain same irrespective of the direction. I'm considering the same. So do I have any glass?
No.
No, there is no pink marking only. So this entire area
Mm.
of the red color area, what we are doing air conditioning, we don't have any this thing. So automatically this value is 0. So obviously area becomes, but I'll just give the delta T over here. Anyway, I have it karke. Actually, it's not required. So delta T in south is how much? That is also 11.
11.
11. And the last one we have is towards west direction. This is equation 2c. And the last one is sensibility gain due to sensibility gain due to exposed gas in west. What is the area? How many glass are there? 1, 2, 3, 4, 5. 5 into 25, isn't it? 5 into 25 square feet. Delta T we have to see. What is the delta T value? So delta T value, if you take it in west direction, that is 163. You agree? So we'll choose
163.
163 over here. So this is our 163. So automatically you'll get 2D. Understood? So now we have to calculate sensible heat gain due to exposed glass. That all glass is still pending, don't worry. Or we'll add all glass over here itself. Yeah.
Yeah.
So sensible heat gain due to sensible heat gain due to exposed due to all glass. All glasses because of the temperature. Till now, whatever we have done it is purely because of light only. You agree? Because of shade and all we have considered. But now we have to consider just because of U factor, thermal quotient factor. So this factor depends again on the the this thing what do you call the temperature difference between inside and outside. So this is a shading quotient, but it depends on the type of. For example, if you use vacuum glass nowadays, you have for buildings and all you use this double glaze and vacuum glasses where all glass will automatically become zero. Understood? Because there won't be any light that is entering in. Sorry, there won't be any heat that's entering because between two panes back you have vacuum. Only convection is there, which is not even convection. Sorry, only radiation is there, which is like very minor value. The maximum conduction, convection, both the values will be zero. Understood or not? That means generally in a glass nowadays for exposed glasses, if this is your sorry, if this is your door frame, You have one pane of gas like this, one pane of glass like this, and then again you have a this is different. So in between, this entire thing is made with second. Epic point. So this is epic points is based on. So let's check. It's not happening, but weird. Okay. Anyway. So this entire hatched area will be made with vacuum. So you have two layers of glass. Inside this, you have vacuum. So because of this, even though you have high temperature here and lower temperature on the other side, you will not have any heat transfer due to conduction or convection. It's only the radiation that will come into picture. Understood or not? Hello?
Yeah. Okay.
Yeah. Else, you have to calculate the U factor of glass and all. So if you consider, because we have already considered single pane gas, the value we will consider is 1.13, which is standard for most of the glasses. Okay. So sensible heat gain due to this one, we can calculate using this value, but only thing we will modify this equation. Q is equal to UA delta T, but here I'll use capital T. Capital T use your indoor minus outdoor condition. You agree? So this is 1.13, which is the physical property of glass or constant that we use in most of the cases. Constant. And then area of the glass is summation of all the areas. This is sum of all the areas, total areas. Okay. Sum of all exposed glasses, area exposed glasses, exposed. Okay. And then this is nothing
Mm.
but is equal to summation of this one plus this guy plus. So this is your total area that we get it. And then you will get nothing but your delta T value, which is inside minus outside. So this is equal to, we have already calculated initially the difference, yes or no? Outside minus inside yesterday. So that particular
Yes.
value, and then we'll get your Q factor automatically. Q is equal to UA delta T, which is 8172.6 is the total value that you've got. Understood? So this I'll write it as equation 2E. So sensible heat gain due to exposed glass, if we take it, sensible heat gain due to exposed glass. Sensible heat gain due to exposed glass. Sensible heat gain due to exposed glass is the total value that we have to take it. Then sensible heat gain due to exposed glass is nothing but your total value, which is the same. Equation 2A plus 2B plus 2C plus 2D. Where is it? It's over here, right? We will maintain the same cell so that it will be easy plus is equal to this guy plus this guy plus this guy plus plus okay, exposed glass also we have added alva. So sorry, all glass also. So totally five equations we have it. So this is nothing but the total value that we have it, which is your NBTU per R, and this is equation 2. Good enough? Able to understand or not? So we got sensible heat gain due to exposed glass as well. Clear? Hello?
Yes, sir.
Yeah. So this is nothing but sensible heat gain due to exposed glass that we have got it. That is equation 2. Now what we have to do, we have to work on the next one, next parameter, which is sensible heat gain due to partition wall, and then it will be partition glass. Okay. So when we consider partition wall here, always remember whichever is separating AC space and non-AC space is nothing but your partition wall or a glass, no matter what. Now, for example, uh, this conference room is separate AC. So this particular wall, can I consider this? I'll highlight a wall again. Just a sec. Uh, but 6 inches, 6 inches. Yeah. This particular wall that I've highlighted, is this a partition wall or not? This is air
Yes, sir.
conditioning space, and this is a separate AC we have it. Is it a partition wall?
If you, yes, sir. Partition wall only.
Uh, okay. Why is it partition wall? Because both are air conditioned spaces, right? This
No,
and this.
one first you have to install one side, no, sir.
First, you have to install it means it's not that like you will do it this and next year you will install one more AC. No, you'll install the AC at the same time only. You'll commission the entire space at the same time.
If both side AC is there, means it is not partition wall.
It is not a partition. There won't be any heat transfer. You agree?
Yes.
But let's say, but can you give a guarantee that like when the client is using workspaces, the conference will always be held
No, conference whenever the meeting is scheduled, that only there is no
that
AC.
time? So worst case scenario, it could be off as well. You agree?
Yes. Yes.
Right. So we have to consider it as a partition wall. Though it's air conditioned space, you have to understand whether during normal conditions it will be on or not. So what I'll do is I'll just highlight all the partition walls. Okay. And then I've got this one. Server room, it will be separate AC, but server room will it be air conditioned or not?
Yeah, 24/7.
24/7, always your AC will be on. So do I have to really worry about your this particular wall?
No, no.
No. No.
No, that's the reason I didn't draw it. Is there any other partition wall? These cabin walls, is it partition wall or not?
Yes.
So I have to take these walls as well? Come
Hmm.
on, it's a part of our air
Yeah.
conditioned space only. So why will internal wall will be a partition wall? I don't have a separate AC for the cabins, right? It's a centralized air conditioning system. Yes or
Okay.
no?
Yes.
Hmm.
So considering these things, so only these are the total partition walls. You agree?
Yes.
So now I have to calculate the total area. This length plus this length plus this length. I've got a small what do you call uh, uh, a small auto Lisp program. So I'm just lazy to calculate it every time. So what I have to do is load close.
CLC.
So I'll just use the TL command. So automatically I'll get the total length, which is around 141 feet, 2 feet, 7 by 16. So around 142 feet. Shall I take it approximately? Yes or no? So total length of our partition wall is around 141.2 or 142.5. I'll take it for our rough calculations. You agree? So for this, we have to calculate it. So anyway, sensible heat gain, the next one is sensible heat gain due to partition wall, which is Q is equal to UA delta T minus 5 degrees. Remember this? I've explained to you during the explanation why minus 5 will take it because compared to outside air, we consider inside the room space the temperature is 5 degrees lesser, 5 degree Fahrenheit lesser. That's the reason. So we have to calculate your U value. U value. Then you have to take it your A value, delta T value, and this one, delta T. This is capital T, alva. Capital T. Temperature difference between inside and outside. Right. So delta T, and then it will be your thing. So first and foremost thing is your U factor of your partition wall. So we'll again go to the data sheet. You're able to follow or not? Yes, please respond.
Yes, following, sir.
So we have to go to partition wall. That's dark equal exposure equivalent temperature difference. There's internet correction in equivalent temperature difference. Yes, this was internet masonry wall. Quotient through this thing. Then you have yeah, this is a partition wall we can consider. Okay, we have, of course, we have got different types of material. So we will take this, let's say I'll use hollow block work. Is it okay?
The
For intermediate walls?
page number, sir.
That's page number 19. Right, so page number 19, if you see transition quotient through Mansari partitions, so we can take, let's say, 4 inches thick as your partition, and I've got like 5/8 the plaster with kind of sand aggregate on both the sides. So automatically it is 0.37. You need not use gypsum. You agree? No one will use gypsum if you make it with block work. So can I consider this or not? Of course, most of the cases you will just use gypsum. That's the other part. You can make even solid gypsum plaster or hollow gypsum tile like that also you can consider. So whatever material you're choosing it with. Am I clear?
Yes.
Hello. So you have to choose a material to calculate. So for me, I've considered this as block work, but of course, in most of the cases, it will be done even with 90% of the time, it will be gypsum itself. But anyway, so 5/8 the plaster, if you consider with this thing, what do you call with the plaster on both the sides for 4 inches, it is 0.37, right? So 0.37, I'll take it as. So this value is 0.37. This depends on your material actually. Then coming, this is how much? Page number 19, Alva.
Oh, yes, sir.
Then coming to area. Area of the partition wall, we have already got it. How much was area?
140.
141.3 is equal to 141.3 feet into bottom of the slab. I have to take it. Yes or no? What is bottom of the slab? We got it? 13 feet, right?
Yes.
Is it 13 feet? Just a sec. I'll write it here. Yeah, into 13, yes. Anyway, I'll write here as well the basic details like Altair, Altair.
4 inches. Both sides.
I didn't understand. So bottom of the slab is how much? 13 feet. Whereas bottom of the fall ceiling is 9 feet up tall, right? Should I remember? Yeah, 9 feet. It's okay. 9 feet. Okay. So these are the data problems. Anyway, so this is your delta T value. Delta T value we have to calculate it. Delta T minus phi I can directly take it. You agree? So delta T minus phi. So that's nothing but is equal to delta T is this value minus phi. So automatically we will get your delta T minus phi. So Q is equal to UA delta T minus phi is equal to U into area into delta T minus phi. Automatically we'll get this value. Right. So this I'll directly take it as your equation. Sorry, sensible heat gain due to partition wall is nothing but this value. You agree? This I can write it as equation is equal to this value anyway. So we'll write it here. Sensible heat gain due to partition wall. Sensible, because all yellow ones, it will be easier for me to do it. Sensible heat gain due to partition wall. Partition wall. So that is nothing but is equal to this guy. We'll write it as equation 3. Equation 3. Understood? So this is sensible heat gain due to partition wall. So let's check. Take it in. So we'll get this value as well. Then coming to the next element that we have is sensible heat gain due to partition wall is done. Now we have to make partition glass or not, if we have any. So AC space and
No,
non-AC space, I can always call it as partition glass. So don't you think this piece of glass I can make it as partition glass or not? Hello?
hmm.
So whichever glass is there on partition wall, I can. Hey, by the way, my mistake. Actually, we didn't minus the area of the glass. Really sorry. We have to minus the area as well. You agree?
Yes, sir.
Which I forgot. Minus of. Sorry. Minus of. We will take three glasses. 10 into 8. That means 80 square feet, alva. 80 plus. Don't you think here we have any glass? This is 20 into 8 is how much? How much is 20 into 8? Anyway.
160.
So automatically we get the area is 1539. So whatever this value is, we'll calculate it separately. Control C. So this is nothing but is equal to this one. So 240 square feet is the exposed, like partition glass area. You agree? Two glasses we have got it. One for the conference room and another for this room. Right? So sensible heat gain due to partition glass. So everything will be same except the U factor, which is again a constant value. So here we'll take it as, because this is not delta T minus 5, we'll just use delta T for partition glass because the light emission through that will compensate that for minus 5, which we explained it already. Q is equal to U delta T minus 5, where U factor is 1.13, which is constant. This is not from the page number. This is the generic glass data. From the manufacturer, you'll get it. Area is how much? 240 alva?
240.
240. And delta T we got it. So automatically I got Q value. Q is equal to U delta T. So this is nothing but your equation number, sensible heat gain due to exposed partition glass. Gain due to partition glass. So is equal to this. So I'm making, I'm repeating that line only because so that while adding, I need not search all the yellow ones. I can directly click it. That's the reason, nothing else. So this is your equation number 4. You agree? H. Done. Coming to the next one that we have is sensible heat gain due to. So now we have completed sensible heat gain due to exposed wall, exposed glass, partition wall, partition glass. Now the next element that we have to see is sensible heat gain due to your roof load and floor load. So in this example, what did it tell you? Above floor is not, below floor is non-AC, above floor is AC. So if above floor is air conditioned, do I have a heat load? Do I have any heat transmission?
No.
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 But below floor, do we have any heat transmission?
Yes.
Yes.
Yes. So we have to take sensible heat gain due to floor load. Sensible heat gain due to floor load. Okay, this I didn't change it. My mistake. This is partition glass, and then Q is equal to delta T minus 5
Something
is
confusing.
UA delta
अरे glass and
T.
बड़े चीजें ना 70%.
You know,
No sir, just confusion.
then coming to the next one is sensible heat gain due to partition glass. So, which is done. So now it will be sensible heat gain due to floor load. Sensible heat gain due to floor
Floor
load.
load.
So this is sensible heat gain due to floor load is which is your Q is equal to UA delta T. UA delta T minus 5. Same partition formula only you have to use it, isn't it?
Hmm.
If U is equal to delta T minus 5, U factor, you have to take it differently, which we'll have a discussion. Area is nothing but your area of air conditioned space or not? Total area, total floor area you have to take, isn't it? Whatever
Yeah.
space you're air conditioning. Delta T minus 5 is equal to this one minus 5. So you get this value, and then only this U factor we have to change it according to our requirement. So your U factor, we will directly again take it from your data book. Okay. Look for the page number exactly. This is your, there's something called as a heat flow down and heat flow up. That is what we have to see. Built-up roofing. This is basically for roof load. You pictured roof, ceiling and floor. Okay. Now, when you see the heat, now you tell me whether the heat is flowing towards up direction or down direction.
Up direction.
Up direction, because from floor it is coming towards your room. So that is
Yes.
obviously your heat flow will be from bottom to top. So automatically it will be up direction. You agree? Yes or no? So we have to take this heat flow up, which is page number 22. For ceiling load, you will take heat flow down. Understood? So for floor load, you can take page number 22 as of now. So this is page number 29, right? 22, 29, sorry. Okay, 22, page number 22. U factor, you get page number 22. So this depends again on our material. So we'll consider 6 inches thick wall, 6 inches thick slab thickness. Let's take somewhere around some 6 inches, 150 mm. Yeah. So we will take this as like, none or you have this just a sec, floral lime, plywood, wooden block, uh, concrete subfloor. We have to take none. Like we've got some concrete subfloor with sand aggregate, and the thickness is 6 inches. So generally we do plastering, and above people will generally go for tiles or not, a half-inch tile. I mean, for floor finish, you have to do, right, something or the other. Don't you think we'll go for some kind of tiling works?
Yes.
So we consider some kind of tiles with this. So this value will be 0.34. Understood or not? Hello?
Yes sir.
So considering this, we have this value is 0.34 as your U factor because of your floor load. 0.34. 0.34. And then area, delta T minus 5, we already got it. So you get this equation. So sensible heat gain due to partition, sorry, due to ceiling, due to floor load, sorry, floor load, which is nothing but your equation of this guy. It's not confusing, right?
Sir, if we view factor while selecting something, we missed it. It is effective calculation, sir.
Yes, obviously. But don't worry,
Instead of
generally what we use, we
0.34 and
always
point
go
0.3,
for, I can get you, sorry.
instead of 0.34, we take an upper value, 0.37, like that.
Your heat load estimation will be more.
Uh,
See, generally, this manually we do it. For most of the cases, you need not even do manually. You have a software called as HAPS, which I'll be teaching in later stage. Okay.
okay.
And you have one more Excel sheet. By default, all the U factor is filled for all the generic materials.
Okay.
Okay. So you need not really change unless the architect clearly specifies it.
Okay.
And if you see any ER books, I mean, there is something called as a, of course, for smaller projects, you don't have anything as such. I agree. Because currently, as I've told you, I'm working in the airport sector. So whenever we award a job, we basically provide something called as employer requirements book, ER book, we call it as. So in
Okay.
the ER book, we clearly specify, all the civil team will clearly specify what are the materials along with the U factors that we have to consider. So directly we
Okay.
take that from that ER book, employer's requirement book. Understood?
Okay. Yes.
Okay, that's how we basically do it. I'll just try to show it. I don't know whether I have earbooks or not because it's my personal laptop. Just a sec. All data. Volumes. So like that, generally we basically make the specifications book, employer requirements book, we call it as. So inside the employer requirements book, you will actually provide a U factor.
Okay.
Either in this one or in the civil book, we generally make it. Oh yeah, like this we'll provide it. Directly we will tell it, okay, you have to consider this. Understood? Clear? So directly you can get the values from the employer, but of course it's only for the standard jobs, not for all the projects that you get it. Okay. Hello.
Yes, sir.
That is nothing but your sensible heat gain due to flow load. We got it, which is equation number 5. We have to calculate for flow load, which is done. Once this is done, then we'll be working on something called as sensible heat gain due to. So floor load is done. So roof load is done. Roof load is 0 anyway, so we don't have anything. Now, don't you think we have completed all the civil structures?
Yes.
Now, what we have to calculate? Sensible heat gain due to people. Just a second now. Current is, yeah. Sensible heat gain due to people. So that is nothing but Q is equal to number of people into Q is equal to number of people into BP per hour or heat dissipation per person. Heat dissipation per person. Yeah. So that this particular value will give you total heat content, as simple as that. So automatically we'll get number of people. So number of people you will be able to get it from here. So let's say how many people are there? Here I've got 130 people. You agree? In the workstation area. I have to calculate the number of seats anyway. 130 people. Reception, don't you think outside people can come? Just a
Yes.
second. Rivali, Rivali, తీసుకోవా బాబుని please. Just a sec, guys. Sorry.
that ఉంది.
ఒకసారి తీసుకోవరా నేను ఇది వేసేసిన డోర్ వేసేస్తాను. తీసుకో నీ మీద వేసా. I'm locking it from outside. Is it okay? Yeah, sorry guys. Yeah, I'm audible now?
Yes.
So, okay. Anyway, so number of people we have to calculate it. So that obviously you have to calculate according to the number of seating which have already done it. So I've considered
Yeah.
130 people over here.
Yeah.
So number of people is 130, and reception outsiders only will come and sit in the sofa, right? Generally,
Yes.
those
Outside
people.
and reception.
Outsiders. So basically, this will take it. And in discussion room, generally at least 1 or 2 discussion room is basically made for external people as well. Okay, that means externally people can come and discuss over here. So we can take even one discussion room at least as external people. So we can take it as how many is equal to 130. This is equal to 130 plus. I've got reception 6 guys plus
Three.
discussion room plus 4
Yes.
plus along with that. Now, don't you think you have your manager room out of this one person will be sitting over other 3 people means here any of these 3 people only will join. You agree?
Yes.
Unless it's a public space like banks where outsiders can come in. So in these cases, so we need not count these 3. It's only one person over here. Here also it's only 1 year. So 1 plus 1, 2. Okay, because the pantry is not our area, so we need not really worry. So plus 2 people have to add. That's all. You agree or not? So I have to
Yes,
add
sir.
plus 2 people.
Yes.
Plus 2 people will take it. So that is number of people is 142 people. Then coming to the next one is heat dissipation. Heat dissipation. So heat dissipation per person, you or I'll write it as heat gain per person or heat dissipation actually. So I'll write it over. Heat dissipation per person for page number I require some space. That's the reason. Okay. So this will again get it from the data book, which is in ISHRE as well as this one. In ISHRE also you get all this data. Okay. So you will get your ISHRE data over here. Heat gain due to people. Strings. Yeah, you can see this table. Heat gain due to people. Yes or no?
Yes.
Table 48. That's page number 31. We'll get it. So page number 31. 31, you'll get it. So this value is how much? Okay, this size itself, I'll change it, increase it. It's okay. So heat gain due to people, page number 31, if you choose it. So what is our indoor temperature we got? 73.4. That's nearest to 75 or not?
Yes.
So this one will take it, and according to the type of application. So what is our application? It's office space. You agree?
Yes.
So if you take your this one, so automatically this value will be 245. Am I clear? This
Yes,
U
sir.
factor will be 245, which is sensible heat. Latent heat is 205. So currently we require sensible heat, alva, because we are calculating only sensible heat gain due to people. So this
Yes,
will be
sir.
245. You have to choose it. Clear? But the same persons, if it's heavy work, if they are doing it, then it will be 525 as well for the same temperature. Clear? If you reduce the temperature, the value will keep on increasing, if you can see it. Sorry, if you reduce it a bit like this towards this direction, if you say sensible heat, instead of 245, it will become 285. That's what I explained to theoretically while explanation. Anyway, right now the value we have to take is 245. So this value is 245. So your Q value, what we have to do is equal to UA delta, sorry, number of people into BTU per hour into BTU per hour. So automatically we will get this value. So sensible heat gain due to sensible heat gain due to people. So that is nothing but this guy, which is like our value of this all BTU per hour. This is equation number 6. You agree? Understood or not?
Yes.
Okay, that because of people also we have done. Now, don't you think we have to calculate because of equipment or not? Because of equipment we have to calculate, because of lighting we have to calculate, and because of pressure we have to calculate. Then we will be able to complete total sensible heat load. You agree?
Yeah.
Okay. So first we will calculate sensible heat gain due to equipment. So sensible heat gain due to equipment I have to consider. So what is my total air conditioned space anyway? Isn't it this one? This is the total space of air conditioned, right? Yeah. This is our total area of air conditioned space. So in this case, now we have to calculate heat gain due to equipment. That is nothing but Q is equal to total watts into 3410. 3410. That's conversion factor that we are doing it. So watts, we have to calculate it. Total watts, we have to consider it. Or kilowatts is also fine. So watts into 3.41, kilowatts into 3410. My mistake. Kilowatts into 3410. So we'll calculate kilowatts value. So kilowatts value is nothing but the total equipment, and we have to multiply with the number of wattage per equipment. Generally, if you take it for computer, for desktop computer, we will take approximately around the value of somewhere around some 300 watts per system. Understood? Including monitor, everything together. So we'll directly calculate the total number of this thing. So don't you think here we have got like 30 people in plus 130 people and 130 systems. So you have to consider 130 systems or not? Yeah,
Yes.
is equal to 130 plus. I have one more. So over here I've got 6 people plus 2 systems because this is 3, and I've got 2 systems over this table. So which is plus 2 plus discussion room. I'll have only 4 systems. Means these people only will come maximum. Obviously, I need not recount the number of systems. But whereas in the manager cabin, I have to consider it. So 1 system each plus 2 into I have to multiply with total wattage per system, which is 300 watts. You agree? Divided by 1000 to convert into kilo. So it is 40.2 kilowatts. So Q value is nothing but Q value is nothing but is equal to this value into 3410. So that is nothing but sensible heat gain due to equipment. So sensible heat gain due to equipment is nothing but your is equal to this value. I might have done it in the title, but yeah, it's stupid. So this one is equation number 7. Clear? So this is sensible heat gain due to equipment, which is equation number 7. So we have just calculated the total load and then we have multiplied by 3410. Now what we'll
Sir, in
do,
kilowatt,
we'll calculate
whatever the
sensible heat gain due to lighting. Is that fine?
hello,
Yeah, please tell me.
sir, in the kilowatt, whatever are the values you added, sir, once you just click there.
Total number of computers, and each
Okay,
computer, generally computer dissipation is around 300 watts. We take it.
okay, 300 you
So I've taken
multiply.
total number of computers to 300. I've done it. If
Okay,
you see it in the equations, I've made the number of computers into 300, and that is in watts. So I have to divide it by 1000 to get it in kilo alva.
okay,
ಅದಕ್ಕೆ like 1000 ಅಲ್ಲಿ ಡಿವೈಡ್ ಮಾಡ್ತೀನಿ
okay,
ಅಷ್ಟೇ.
okay.
ಅರ್ಧ ಆಯ್ತಲ್ವಾ?
Okay.
Okay. So then Q is equal to kilowatts into 3410. I'll get the total value.
Yeah.
And coming to the next one that we have is sensible heat gain due to equipment once it's done. Then we'll be working on sensible heat gain due to lighting. Sensible heat gain due to lighting. That is nothing but Q is equal to wattage per SFT, wattage per SFT, because if the electrical drawing is already there with you, nothing as such. But you will not have it, so that's the reason, into wattage per square feet into area into 3.41 will directly give you. You agree? So wattage per SFT, according to the type of lighting you will take it, area, and then you will get the Q factor directly. So wattage per square feet, the general value we take for LEDs 1 or 1.25 max. So 1 is sufficient nowadays because of higher efficiencies. Okay. So we'll take 1. But for retail sector and all, you will take even 2.5 or 3, 3.5 as well. Understood? It depends on the illumination level that you're looking for. Clear? Hello.
Sir.
Okay. So this generally you take it as 1 feet. Area of our space we already know. Area of air conditioned space, which is 5900 SFT. And then coming to Q value is equal to this into 3.41. You will get the total value, which is this one. So which is your Q value, sensible heat gain due to lighting. Gain due to lighting. Sensible heat gain due to lighting is equal to this one. You'll get it. Which is equation number 8. Here, Alt H. So this sensible heat gain due to lighting, we get it. So once after this sensible heat gain due to lighting, then we'll be working on the next element, which is sensible heat gain due to pressure. You agree?
Yes.
Amount of pressure. But before calculating sensible heat gain due to pressure, don't you think we are supposed to calculate the amount volume of fresh air or not? Right. So for that reason, we will calculate what is the volume of fresh air that we basically require. So volume of fresh air is outside recipient. So quantity of pressure. So for that, we will have nothing but a method 1. Method 01. Method 01, we will calculate it according to method 01, we will calculate according to CFM per square feet plus area. Right? Method 1 is CFM per SFT into area plus number of people into CFM per person. CFM per person. That's what we have to do. Understood? Okay, so this is our first method. Method 1 is CFM is equal to area into CFM per square feet plus number of people into CFM per person. And method 2 is as per air changes. As per air changes. Air changes per hour. Yeah. So first I'll start with method 1. So method 1, first we will calculate CFM per square feet into area. So first we will calculate CFM per square feet and area. Anyway, CFM per SFT. This we get it from a data book again. I'll write the and area we already know. Then we'll get number of people. Okay. Then it will be CFM per person. CFM per person. Both will get the value from our data books. So this CFM per square feet, according to the office area, we have to take it, right? So this we get it from this one. Solar heat gain from rested application. That's okay. This one heat gain due to miscellaneous applications, electrical motors. There we go. Yeah, this is a ventilation standards we use it. Okay. So this particular thing, if you take it, ventilation standards, that is page number 30 over here. Okay. So this is nothing but your page number 30, you get it CFM per person as well as CFM per SFT of floor. Okay. This is page number 30. Both we will get it from page number 30. Page 30. Sorry, not this one. CFM per square feet into area, number of people illa. CFM per person, you get it. This is as per site condition, alva?
Yes.
Number of people. Right. So CFM per square feet, we get it from page number 30. So this one, what we will do is CFM for square feet, this is office area. So we have to refer office area. So this particular one, we can see it. Right. So this is CFM per square feet. If you take it, you will get a value of 0.25. You agree?
Yes.
But please consider this is not the exact value. You have to actually refer ISHRE handbook. Then it will be different. So after this, I'll take speak of ISHRE. As we are just using this old data book, I'm just showing you using this one. But using ISHRE, you have one more page number which I'll be showing you. Don't worry. Take it. Format, everything is same. It's only the numbers will vary. Currently, we'll take 0.25.
Yeah.
Yes. So we'll take it as 0.25. So is equal to 0.25. We'll take it. Okay. Then coming to the next one is area. So area is how much?
5900.
5900. I'll directly take it from here. And then you've got number of people. Number of people are how many? We already calculated, Alva.
140.
Due to number of people, yeah, 142. We got it. And then CFM per person. CFM per person, you get it again for the same location only. Office area, this is the recommended value. If you take it, is around general. Obviously, you will tell me this is wrong. Actually, 15 CFM is more than adequate. This is very as I told you, this is very old data because now the data has been changed a lot. Instead of 15 CFM is not really required for an office workers. If you take it, somewhere around 7.5 CFM per person is sufficient. Understood? But anyway, I'll show you the reference data in the ISHRE handbook. Don't worry. As of now, we'll take around 15.
Yeah.
Okay, this is also on very high side anyway. This will get. Then we will get this value as method 1, method 01. So in this, what we'll do is equal to CFM per square feet into area plus number of people into CFM per person. You'll automatically get this value. This is method 1. Set H1. Yeah. So this is method 1. Now, don't you think we'll calculate according to air changes or not? So, which is not an official method as I've told you, but we generally use it. So, this unit is CFM anyway. CFM, cubic feet per minute. Okay. Then coming to the next one that we have is method 2, which is as per air changes per hour. ACPH, unless specified, generally we take 1 in any of the cases. Understood? 1 air changes, that means in an hour, the total volume of air that you wanted to replace is 1 time. Understood? Am I clear? So,
Yes, sir. Yes, sir.
and get you sorry?
Yes, sir. Yes.
Okay. So method 2, as per air changes per hour. So here the formula that we do it, I'll directly write the formula instead of this one. Volume into ACPH divided by 60. That's how the formula will be. So ACPH is 1, volume of the room. A volume of the room will be how much? Is equal to area into height or not? 13. You agree? Which is our bottom of the slab. Yes or no?
Yes.
So this is the volume. Then method 2's value will be Control C, Control V is equal to volume into air changes divided by 60. We'll get this value, which is CFM again. So this also will highlight it. Then coming to final quantity of fresh air is max of both the elements. Understood? Max of method 1 and method 2. Max of method 1 and method 2. Yeah. So this value is equal to this one is equal to max of method 1 comma method 2. So automatically this value is our CFM in this entire project from now on. Understood or not?
That is
Yeah. Understood?
Thanks.
Huh?
Okay.
Oh, okay, speaking with someone else. Take it. So now we'll be working. Dikshit or Vinodana, whoever is speaking, you can go on mute. I mean, if it's not regarding this. Can we continue?
Yeah.
Now we have to calculate sensible heat gain due to pressure. Sensible heat gain due to pressure. For that, the value is Q is equal to OA CFM. That is nothing but our CFM that you have it. Outside air CFM that I mean to say into 1.08 into delta T. Delta T, have a symbol anyway. Insert symbol, delta T. Delta T. Q is equal to OA CFM into 1.08 into delta T is a value into bypass factor. Bypass factor. You agree? This is the formula that we had a discussion, right? So here OA CFM we know and delta T we know, right? Delta T and then we have bypass factor. So OA CFM is how much? 3605. You agree? Delta T, you know, which is outside minus inside temperature, which is 22.6 anyway. And then you've got bypass factor. So bypass factor is depending on the coil design you have it. Worst case is 0.15. But nowadays you get, because if you consider 4-ray coil or 6-ray coil, it will only be 6% or 7%. It will be 0.06 or 0.07 as well. But for our design purposes, I'll take 0.15, 15%. Is it okay? I know it's very on the high end, but we'll be safer that way. Clear? Understood or not?
Yes, sir.
So Q is equal to Q, how will you calculate it? Simple, is equal to OACFM into
1.08.
delta T into bypass factor into 1.08.
1.08.
Yeah, I'm doing that as well. That's a constant. Clear?
Yes.
So this will get it as your Q factor. So sensible heat gain due to pressure, sensible heat gain due to pressure. Pressure is how much? Is it this one? Sorry.
15,198.
Yeah, this equation alwa. This is the line, right? Huh. Is equal to this particular one, BTU per R. BTU per R is a value. Equation is how much? Equation number 9. Can you take it?
Yes.
Equation number 9. Sensibly give you pressure. So I'll make it with L. Is it clear? This cell, write this over here. I guess this is better. Is equal to max of. While adding, I don't want to mess it up. That's the reason. Comma. And this one. Method 2. Okay. I'll take it. Is equal to this guy. Yeah, just a sec. Huh? Yes. So, yeah. So automatically we'll get this value, which is uh, there is a CFM over here. There is OA CFM, outside is CFM. Yeah, three. This is a value anyway. Here also we've taken it, right? Perfect. So this is nothing but your sensible heat gain due to pressure. So once this is done, then we'll be calculating to the next element, which is sensible heat gain due to, so sensible heat gain due to pressure is over, equipment is over, people are over. Is there anything else that's left? Nothing, right? Civil we have completed, occupants we have completed, lighting we have completed, equipment we have completed, pressure we have completed. So don't you think we have completed the total sensible heat gain? Yes or no?
Yes.
So we'll write it as room sensible heat gain. So room sensible heat gain is nothing but your summation of equation 1 to uh, insert symbol. Your summation of 1 to 9. So that's nothing but I can add it over is equal to sum of. That's the reason I've actually done it separately so that I need not search. Oh, okay. This particular dotted, it might not be able to tell. Pa. Sorry. It's dotted. If it's there, no, it will not count.
Okay.
Oh, it has counted it. Good. Good, good, good. I thought dotted, it will show an error. I was under impression. Anyway, let me just check it once again. It shouldn't consider it as minus. That's the reason. Yeah. So total 300152. 300152. Alva? Yeah, 300152 is the total value, is BTU per hour, is nothing but your this one, which is effective room sensible heat load. Okay, this particular one is effective room sensible heat load. Now I have to calculate something called as this is room sensible heat load. Now I have to calculate effective room sensible heat load. Effective room sensible heat load. Can I go to that room? Effective room sensible heat load is equal to, how will we calculate is effective room sensible heat load is equal to room sensible heat load into 1.1. That means 10% we are adding it. That's all. So this value is equal to this into 1.1. Understood or not?
Yes. That is
Yeah.
factor of safety,
So
sir.
this is factor of safety. Yes, including the factor of safety, we are doing it. 10% as a factor of
Excuse
safety.
me.
So yeah, tell me.
No, sorry to interrupt you.
Huh? I didn't get you. Sorry, your voice is unclear, buddy. Would you mind repeating it?
Hello.
Hello.
Yeah, I
Yeah,
need to leave now.
please tell me.
I need to leave now.
Yeah, yeah, you already told me. You already told me.
If
Or
possible, shall we
for everyone, shall we continue tomorrow, or is it okay
sorry?
if I continue without notepad?
Yeah.
We'll continue, or you want me to continue from tomorrow again? I mean, your call. I don't mind anything.
This problem is completed or it will take time.
It will take probably other half an hour.
You continue now, just
Yeah,
share
yeah, continue.
the lecture.
Huh? And get you, sorry.
We'll close this problem, sir.
Oh, we'll complete the problem. That's good.
Yeah, yeah.
Okay. So we got this effective room sensible heat load is room sensible heat load into 10%. So that we got it as this thing, which is equation A. I'll write it. Clear? Now next element that we have to do is latent heat gain. Don't you think you have to calculate or not? Yeah.
Yes.
So now we will calculate something called as latent heat gain values. So again, we will start with latent heat gain. So latent heat gain, we have got only two things. One is because of people and other is because of pressure. So latent heat gain heat gain due to people. So latent heat gain due to people. Yeah. So latent heat gain due to people is equal to number of people into BTU per person. BTU per person. Now, number of people we can calculate number of people.
142.
People we already know. What is the numbers? In the
142.
previous one we have calculated, right? How much is the total number of people?
142.
142. Right. Number of people is 142, and then BTU per person or heat dissipation, sensible heat dissipation. Sensible heat dissipation.
Page number 31.
Okay, page number 31 alva.
Yeah.
Page number 31 will take it. So automatically we'll get the value from here only. So we can again take latent heat. So which is 245 and this value is 205. Latent heat is 205. So we can directly take it as 205. So we'll get sensible heat gain due to latent heat gain. Due to people is due to people. Latent heat gain due to people will be nothing but your is equal to number of people into this one. You agree?
Yes.
This I'll take it as equation. Chapo. This is the line. This. Okay. So this one we will directly take it as equation number. Again, we have to give a different number. Or again, is it okay if I make it with 1? Or it will be confusing? Huh?
Otherwise, the same number will be, sir. Like whatever sensible it due to
That's
people
what.
we have given, that A will
Okay,
be.
that it will be much more confusing, no? Because we will add it. Actually, those two we don't add it. So once this effective room is there, so we will not be using the above equations at all. Mugittu ಅಷ್ಟೇ.
A
One day you
will
want me
be.
to prove? A already we have provided over here, no?
No,
That's the
not
reason.
like that. If it is sensibility gain is 7 means we'll give that latent heat give to people 7A.
Okay, like that you wanted to. Or else
Yeah,
we'll continue the numbers, no, Mugittu?
yeah, that is
We'll
okay.
continue the numbers.
Yeah.
That's better. So this is equation number 10. And then we have to consider latent heat gain due to people is done. Now what we have to do, we have to calculate latent heat gain due to fresh air. Latent heat gain due to fresh air. Latent heat gain due to fresh air. Due to fresh air. Fresh air. So latent heat gain due to fresh air is nothing but number of that equation also, I'll write it over here itself, is equal to OACFM into latent heat gain due to fresh air is nothing but OACFM into 0.68 into delta humidity ratio into bypass factor. Bypass factor into not 1 minus bypass factor, no. That is after, at last we will have it. That is one more thing that I'll explain you. Due to fresh air, that is this particular one is fresh air that is not touching the coil. It will be because of touching the coil. That we'll calculate it separately anyway. Understood? So bypass factor into, we have to calculate the delta HR. You agree?
Yes.
Insert symbols delta. Yeah.
Here we don't do again method 1 and method 2, sir.
Already we know OACFM for the entire project. It will be same, alwa.
Okay.
Why should we do it again? Right. Bypass factor we know it. Bypass factor we know it, and then delta HR also we know it. So symbol delta HR. And understand, buddy? Sorry, didn't understand.
Sorry, sir. Here is something.
Okay, take it. So here we'll directly calculate the fresh air volume, exposed glass. Where is it? Quantity of fresh air CFM is this one, and then we know the bypass factor is 0.15, and delta HR we get it from this data. Listen, this is your humidity ratio 55 that we got it from the inside minus outside. Then what we'll do, latent heat gain due to pressure. So latent heat gain due to fresh air is equal to, automatically we'll get it here, LHG, latent heat gain due to fresh air. Pressure. So that is nothing but your equation again will be is equal to OACFM into bypass factor into delta HR into 0.68. That will basically give me your equation of 11. You agree? Is there anything else because of which I have a latent heat? Don't you think we have completed it or not? Hello?
Sir.
I'm audible?
Hello?
Yeah, I'm audible?
Yeah, audible, sir.
Okay. So don't you think anything, do you think anything else is required or it's sufficient? So obviously this is the total heat load that we got it because of people and because of fresh air.
Pressure.
Okay. Now what we have to do, we have to calculate total room latent heat load. Room latent heat load. So room latent heat load. That is nothing but your summation of one, equation number, these two elements we have to consider. Equation number 11 and 12. 11 to 12. You agree? That's nothing but is equal to this guy plus this guy.
11 to
So that we will take it as equation number. So this I'll write it as equation number B. Is it fine? Not this one, sorry. It's still, it's there. We have to calculate a factor of safety anyway. So now we have to calculate effective room latent heat load. Understood? So let me put the gap here. So it's exactly not. So effective room latent heat load, we'll take it as, we'll not call it as sensible. This is latent heat load. Latent heat load. room latent heat load into 5% we take it for latent generally. 10 is not required. 0.5 will take it. So this will multiply it with 1.05. 0.05. Understood. So automatically you get this value. This I'll take it as equation B. Am I clear or not? Yeah.
Yes, sir.
Now coming to the next one that we have is so we have
Room
calculated.
latent it 11 to sum of 11 to 12 is written, sir. 12 is not
Yes.
the
Oh, okay.
equation.
10 to 11. My mistake.
Okay.
Sorry. 10 to 11. Yeah, equation 9, 10 to 11. That's it. Then coming to the next one that we have to do is we have to calculate the next element, which is after effective room latent heat load, we will be calculating something called as room sensible heat load. We have to calculate effective room late sensible heat load, latent heat load is done. Now we have to calculate heat gain due to fresh air, which is touching the coil. Now, not touching the coil, we've already done it, isn't it? Now we will calculate something called as which is touching the coil. So sensible heat gain due to fresh air, which is touching the coil. We require this data for calculation of a CFM, of course, due for heat load as well. Okay. So sensible heat gain due to fresh air that is touching the coil. The formula is what? Is equal to OA CFM into 1.08 into delta T
1 minus
into 1 minus
bypass
bypass factor
factor.
is what we will use it. Delta T into 1 minus bypass factor. 1 minus bypass factor will take.
Bypass factor.
So here will we already know the OACFM values and all? Yes. OACFM, bypass factor and delta T, we know all these values. So sensible heat gain, so that is Q value anyway. OACFM we know. Delta T we know. This is capital T anyway. Delta T is because small t it was always used for equivalent temperature difference anyway. That's the reason. Then again we know delta T value. Bypass factor also we are aware of. You agree? So delta T is how much? 22.6.
22.6.
And bypass factor is 0.15, 15%. Then OACFM we already know which is this value 3605, the green value. So Q value, sensible heat gain due to fresh air, is due to touching the coil. Q, if you calculate it, that will be nothing but is equal to OACFM into delta T into 1 minus bypass factor into 1 minus bypass factor into 1.08. You agree? This I'll take it as equation 12. I'll take it. Okay. Understood or not?
Yes, yes.
Okay. Then coming to the next one that we take it is sensible. This also I'll make it as yellow. Sensible heat gain due to coil load. This is the value. Then coming to the next one we have to do is after sensible heat gain due to air touching the coil, we'll calculate something called as this one latent heat gain due to latent heat gain due to pressure touching the coil. Latent heat gain due to pressure touching the coil. So that is nothing but Q is equal to 1.08 less 0.68 into 0.68 into delta humidity ratio into 1 minus bypass factor. You agree? So we know these values anyway. Of course, this is not CFM. This is equal to outside air CFM. And then we have got delta T is equal to, this is actually delta HR anyway. Humidity ratio, then is equal to humidity ratio. Again, from the start of the table, we know it. Outside minutes, inside humidity ratio, and bypass factor is this one. So Q is equal to, that's nothing but the total heat gain because of that, is equal to OACFM into delta HR into 0.68 into 1 minus bypass factor, 1 minus 0.15. You agree? That will give equation number 13. Clear or not?
Yes.
Now we will calculate something called as grand total heat load. Grand total heat load. Total heat load. That is nothing but your equations of, that's nothing but summation of, just a sec, sorry. Yeah. So we have got summation of equation A plus A comma B comma 12 comma 13. These are the equations that we have to add. Understood or not? That's nothing but is equal to this one plus this one plus this one plus we have got this one as well. Clear?
Yes.
Yeah. Effective room circular load, effective room latent heat load, and these particular values. Then you will get this one, which is okay. This will ignore it. Then coming to effective grand total heat load. I mean, we'll take other 5% extra, nothing else. Effective grand total heat load. That is nothing but grand total heat load. Grand total heat load into 1.05. That's nothing but is equal to this value into 1.05. So this is the final value that we have it. Understood or not? Hello?
Yes, sir.
This is our main equation that we have it. Clear?
Yes.
All units are BT per hour, BT per hour in this particular values. Don't worry. Okay. Just a second. Really. Okay, you will get this BT per hour. So this one will directly take it over here. BT per hour. I mean, all these equations have BT per hour. Later on, I'll share it. Don't worry. Okay. So now tonnage is equal to TR is equal to what is the value of BT per hour divided by 12,000 or not?
12,000. Yes.
So you got 49.99 tons. So approximately we can round off to this value, which is this one, round up of this value, we can directly do it. $50 tons. Understood or not?
Yes, sir.
We got this value as total tonnage. Heat load in tons.
Okay.
So this is our final answer. You agree?
Yes, sir.
Okay, so we came to know we have to insert 50 tons of equipment to maintain a 23 degrees centigrade inside a room size. That's one part of the problem. Clear?
Yes.
Now, second part of the problem is to calculate the pressure or the CFM that we require, DCFM value. You agree? So one part of the problem is done, which is heat load. The second part of the problem is the airflow rate that we have to have. Clear? So shall we continue with the airflow rate calculations? CFM, I mean, couple of more formulas, that's it. So dehumidified CFM, the formula that we have is Shivali, please come for 10 minutes only. Take it inside now. So dehumidified CFM is nothing but the total, the formula that we have is CFM into what is the formula? Effective room sensible heat load. You remember this? I taught you. You made a note or not? Hello? You guys made a note of it or not?
Effective room sensible heat divided by 1.068 into 1
1.08
minus
into
BF
1 minus BF into
into
indoor
I
drivable temperature minus
driver
DVT
temperature
minus
into
apparatus dew point temperature. Right? So this is the formula that we have to use it. You agree? So
Yes.
here, effective room sensible heat load, ERS HF, we know it, and bypass factor is a parameter. Indoor drivable temperature, indoor drivable. I'm writing full form so that later on sometime if you have a trouble, you'll remember it. Indoor drivable temperature, and then you have got apparatus dew point temperature. Apparatus dew point temperature. Dew point temperature. Okay. So apparatus dew point temperature. So in this, we'll try to get all the equations here. So effective room sensible heat factor, don't you think you already know it over here? Which is equal to your effective room sensibility heat factor, which is your equation A or not?
Yes.
Is not factor, sorry, effective room sensible heat load minus T. Okay. Then coming to bypass factor, which you are already aware, 0.15 throughout the project. Then coming to the next one is indoor drivable temperature. That also you're aware, which is this one. So only thing that you're not aware is apparatus dew point temperature. Apparatus dew point temperature, you will get it from this particular page number. Just a sec. But that again depends on two parameters. One is indoor drivable temperature and room conditions and effective room sensible heat factor. That will give you apparatus dew point temperature. Understood? That is from page number 37 to 39. 37 to 39, you'll get it. Page number 37 to 39. 37 to 39. Okay. So this will give you these values. So this, as I've told you, it again depends on indoor drivable temperature, which you're already aware of, IDBT. DBT, drivable temperature. Okay. And something called as effective room sensible heat factor. Okay. Effective room sensible heat factor, which is nothing but equation A by A plus B. Effective room sensible heat load by effective room sensible heat load plus effective room latent heat load. Understood or not? Hello? Guys, able to follow?
Yes, follow it.
Okay. Is equal to equation A is where this one is equation A divided by equation A plus B. A plus equation B. So that means 86, 0.8. That means in the total heat, almost 86% is sensible heat, remaining percentage is latent heat. You agree or not? Clear? Now, we have to calculate according to these values. This is a factor which doesn't have any units anyway. Bypass factor doesn't have. This is degree Fahrenheit, which you're already aware of. I didn't write units everywhere. You're able to manage it, right? Yeah? Hello?
Hello, sir.
Yeah, you're able to follow it, right? Now
Yeah,
coming
follow.
to the next one, we have to calculate it using your, you're telling something? Sorry?
No, following like this.
Now coming to the next one is we have to calculate according to our indoor tribal temperature. Your indoor tribal temperature is how much? 73.4, alva. You want to maintain 73.4 degrees centigrade, sorry, degree Fahrenheit. Now we have to calculate your indoor conditions, which is indoor tribal temperature. So this is not mistake, that is delta T we have taken. This is IDPT we have to take, which is indoor tribal temperature is 73.4. You agree? Now we have to calculate something called as apparatus dew point temperature, which is again dependent on this one and this value. So this we have to refer this sheet. So if you see this sheet, this is your tribal temperature. This is what is the relative humidity that you want to maintain and what is the factor. According to that, you have to choose your right apparatus dew point temperature. Am I clear? Now, what is the value we got it? 73.4, right? Our indoor conditions. So 73.4 means, don't you think it is lying between 72 and 75? Don't you think the number 73.4 is lying between 72 and 75?
Yeah.
So we have to interpolate for 72 and 75, then we'll get for 73.4. But let's see, this effective 0.86, is it available or not? For 75, 50, because our indoor condition is 50, right? For 50, do I have this value of HTD? Factor HTD? 0.86. Do I have 86? 84 is there, 92 is there. So I don't even have 86. So I have to calculate interpolation over here. Then here again, I don't have 0.86. So it again lies between your 88 and 81. We have to calculate 86. And then we have to interpolate between these two values. You agree? Yes or no?
Yes.
So we have to calculate interpolation for the following thing. So we will do the rough calculation over the right hand side. So if I want to calculate your apparatus dew point temperature for 75, what is the value? 75, this is your tribal temperature, dBT. dBT, and this is your RH, 50% relative humidity. This is 50% alva, 50%. So for this one, what is your this value? 0.84 and 92 alva. 0.84, 0.92. 0.92, you have it. For 84, what is the value? 52. You agree? For 92, what is the value? 54. You agree? The value that I require is 0.86 anyway. So let's not worry about it. What we want is 0.86. We'll calculate it. So is equal to this value minus this guy. Is equal to this value minus this guy. Then we'll get for each value if we want to calculate is equal to this value divided by this guy is per one piece. I'll get it. Yes or no?
Yes.
But what I actually require is 0.86 is equal to 0.86. So is equal to, for 0.86 I can write it as 84 plus 2, right? Plus 0.02. You agree?
Yes.
52 plus 0.02 into this one. You agree? So it is 52.5. Yes or no? So for
Yes, sir.
75, we got 52.5. For 75, we got a value of 0.52.5. You agree? Similarly, do you think I can calculate it for 72 interpolation? For 72, 50% RH, luckily we have it. So 72, 52, 50% RH. Again, the value is between 81 and 88. 81 I have to take it. 0.81 I have to take it. and then I have to take it as what is the value? 0.81 and 0.88 alva. 0.88. Sorry, 0.88 horizontal schematic wave is it? 0.81. How much is it? 48. You can read this or not? 48 and 50. 48 and 50 respectively. I'll use the same thing over here. So again, this also I can copy the formula. So automatically I got this value. So is equal to what is the value I required? 0.86 alva. 86 means I can write it as 81 plus 4 plus 0.4 or not?
Yeah.
Is equal to 48 plus 0.04 into sorry 0.05 alva because 0.86. So yeah, 0.05 plus 0.81 into this one. You agree? You will get this value as 49.42. So now I have the value for 75. I have the value for 72. Don't you think you have to get the value for 73.4 or not?
Yeah.
Is equal to this value minus this guy. This value minus this guy. Then I require why it is minus 75 minus 3 is equal to this minus this, right? Yeah, 3.03. So 1 is almost equal to 1. You agree? So I require 73.4. 73.4. How much will it be? Is equal to 72, whatever I have it, plus 1.4 alva. 1.4 into this, the difference between those two elements. So it is around 50.86. So my apparatus point dew point temperature finally is this. Okay. Understood or not? Hello?
Yeah.
Yeah, interpolation, that's all. Plain interpolation we have done it, but only three times we have done it. So here, this is nothing but 50.86 is equal to this value. I'll mark it. So this is our interpolation. So DCFM, now don't you think I can calculate here? Dehumidified CFM? CFM is nothing but, DCFM is nothing but is equal to effective room sensible heat load, which we are already aware of, divided by 1.08, 1.08 into 1 minus bypass factor, 1 minus 0.15 into
Indoor
indoor
driver.
drivable temperature. Indoor drivable temperature minus apparatus dew point temperature. I guess that's a total time. So 15,000 CFM. So I'll round off this value, if that's okay. I'm sorry, I didn't consider the arguments. Comma 0. So 15958 CFM is what we'll require. You agree? So if we select an AHO, it should have around 15,958 means we'll take it around 16,000 CFM, no problem. 50 tons and 16,000 CFM is what we require for this particular area. Am I clear or not?
Yes.
Understood. So this completes our heat load calculations. So I expect you to work on your server room or pantry or any other things. Is it fine?
Yes.
So I'll share you this heat load as well. So tomorrow you guys try it on your own. You can have a group call if you wanted it. So tomorrow we will not take any class. Again from Monday we will continue.
Sir,
I'll
one
clarify
more question.
I'll clarify queries if you have any. Is it fine?
Yeah.
Okay, then
Hello.
we'll do that. Yes, please, Shani.
Sir, Vinod here.
Yeah, hi, hi. Yes,
Sir,
Vinod, please tell me.
actually in our dryer system also like that is there, sir. For paddy drying, moisture
Hmm.
content reducing, we'll give heat
Hmm.
exchanger and blower, sir.
Okay.
In that same concept we can use, sir.
No, there again, you have to calculate according to the moisture content inlet, you have to do it. It's nothing related to your
No,
heat
in
rate.
the whatever last step, two step we got now, sir. Total heat and how much CFM required for that heat reducing.
Yeah, yes, you can use directly this formula. In fact, Q is equal to 1.08 into this delta HR is there, no? That particular
Yeah.
equation, you can use it.
The particular heat, how much CFM required, that formula you can use.
That formula you can use it.
Okay,
Yes.
okay,
If you
sir.
know what is the heat that you have to extract from it, you can use that formula. In fact, it's there even in NBC also.
Okay.
Shall I show you once? In National Building Code, it's available. Just a sec.
Okay.
There's a ventilation topic. All data to read NBC. Volume 2, you have it actually, not in volume 1. There's something called as ventilation. Just a sec. Uh, Part 8, air conditioning. Natural ventilation is there, no? So, in this you have a particular. Sorry. Yeah, in this you have it actually, ventilation topic. This is the general air changes volume as per like this thing. As I told you, for office area we'll consider one, but for remaining things you can take this if it's only ventilation, not air conditioned spaces. Okay, because for transformers and all we'll calculate according to the heat gain actually. Strength. Yeah, this particular formula you can use it. Volume of air required for removing the sensible heat, because it's all sensible heat, right? Is there any moisture content as oh,
Yeah,
moisture content
moisture
is what
content.
you'll actually take it, no?
Latent it, sir. It is have moisture content. They
It
soaked
will have
in
moisture
water and
content.
all.
Then we have to calculate this formula. We already have this delta HR, alva.
Yeah.
So using that equation, you can always do it.
Okay.
So you have to remove the total moisture content. So you have to calculate how much moisture you have to remove it from that particular one grains. Then you can calculate
Yeah.
this equation. Yes. Now the sensible heat, sorry. Yeah, latent heat. Understood?
Yeah. Yes.
Okay. So you've got any queries in this? Anyway, you will
Next,
definitely
we
get
will do one
many when you
problem.
work on the problem.
Yeah. Yes.
I agree. Okay. So I'll share you this Excel sheet as well for your reference.
Okay.
And I'll share you that CAD file as well. CAD file, did
Okay.
I already share it to you? Not yet,
Careful
no?
already shared, sir.
CAD file I already shared, is it? Okay, fine,
Yeah.
fine. Then I'll share you this Excel sheet as well, like, where heat load one karke. So over the same project, we'll try to complete remaining things. For example, like, air distribution, like, VRF system, everything we will solve on the same project. Are you guys
Okay.
okay with this?
Yes, sir. Okay.
Yeah, this is kind of a bit practical itself, so not a problem. Okay,
Okay.
fine. Then we'll meet again on Monday.
Yeah. Yeah. Sure.
See you, Kevin. Bye-bye. Good day. Take
Okay.
care.
Thank you, sir.